Okay, so what is the value of 3 over x as we plug in different values for x? Well, I'm going to go to the table. I've set the table up so instead of going by ones, it goes by smaller increments. It's going by hundreds. So if I start at like negative 0.11, and all I'm doing is I'm just moving my x values along the number line towards 0, right? Negative 0.11 is just over there somewhere. As I step my values closer and closer to 0, look what's happening to the size of the fraction. It's getting bigger, isn't it? Right? It's getting bigger. If I go down, and I keep doing this, it's getting pretty big. At negative 0.01, I'm at 300 is the size of the fraction. When I go to 0, it gives me an error. Okay? And I could make this even smaller. Instead of just limiting myself to going by hundreds, I could go by millions or billions or something like that. If I were to try to do something like this, 3 divided by 1 million, I'd get an answer of 3 million. Right? So what's going to happen in general to the size of a fraction if we keep the top the same but we make the bottom smaller? It's bigger, right? And what's going to happen, is there any limit to how small I can make this number on the bottom? I could choose 1 million, or I could choose 1 trillionth, or I could choose 1 quadrillionth. I could make it as small as I wanted to. What's going to happen progressively to that number on the top as I do this? It's going to get bigger and bigger, isn't it? In fact, it gets bigger faster. Every time I add a 0 to this number on the bottom, the number on the top gets 10 times bigger. So if I had 2 zeros, all of a sudden it's 100 times bigger than it was before. I had an extra one, now it's 1,000 times bigger, right? So it's like a runaway train. What do we call that concept of something that gets bigger and bigger and bigger without ever stopping? There's a word we have, infinity. Yeah, there's a word we have to describe that in math called infinity. And that's why we can't divide by 0, because if we try to divide by 0, as the numbers that we're plugging into the bottom of the fraction approach 0, the fraction as a whole explodes and gets infinitely big, and infinity is not a number. Infinity is out of control. You know, you can't put your finger on it. It's not a concept that we're able to say the answer is infinity and have that be the same thing as saying the answer is 37, right? 37 is a number I can point to. Infinity goes on forever. Infinity is weird. How many numbers are there on the number line, which we're going to now call the real line? Infinite, right? How many numbers are there between 0 and 1 on the number line, just in that one little segment?
Infinite.
Infinite. How many are there between 0 and 0.01? Yeah, strange. That we can subdivide that line as much as we want to, and there's no limit to how many numbers we can choose. Think about this example. This is something we deal with a lot in calculus, is this idea of limits. This is a weird one, and we'll come back to this at some point. But imagine that for now, for eternity, assuming I live forever, I'm going to every second, from here to eternity, yeah, every second, from now to eternity, I'm going to cut my distance to the door in half. Starts to get pretty boring after a while. Do I ever actually get to the door?
Never get that.
I never get to the door. Okay, but if you had to describe one thing that might be what we call the limit of my motion, what would that thing be? What's the only thing that I don't ever actually step on between here and the door? Well, maybe the door is like 0. But I asked that in kind of a confusing way. Would it make sense to you if I said that even though I don't get to the door is the limit of my motion? I can't get to the door, but if I had a really fine point pen, I mean, I don't know where you buy them, if I had a really fine point pen, where I could make points that were infinitely small, if I could really magnify this thing and make a point, is there any point I could ever make on the floor that I wouldn't step on, as long as I didn't draw it on the door?
Yes.
I mean, no matter how close I think I'm getting to the door, wouldn't you agree that if I'm cutting my distance to the door in half every second, eventually I'm going to step on that point, aren't I?
Yeah.
There's no way I could ever draw one that I'm not going to step on. Okay. Well, maybe I could just draw one right next to the door, and that'd be the point right next to the door would be the one I could never step on. But is there such a thing? Is there a point right next to the door? No. There's not. It's not like, if I look at, mathematically, there's no limit to how far I can zoom in on this thing. It's not like you're looking at, like beads on a necklace, and the bead next to the door is the point that's next to it. Because if I just focus in more closely, turns out that how many beads are there between that one and the door? Infinite, right? I can always zoom in more closely on this line between me and the door, and always expose more and more points that I haven't stepped on yet. Weird concept. And so no matter what point I draw on no matter what point I draw on the floor, I'll always step on it, but I'll never get to the door. Weird.
It's like the little color on the color.
Well, yeah, and I mean, it's, this obviously this example is it's a little bit foreign because we don't see that in our everyday lives. And to be full disclosure, if you look at what physicists are now saying, that's probably not the way the universe actually works. Mathematically, it is. Mathematically, on that number line, there's no limit to how much I can zoom in. But probably, and maybe later in the year I'll tell you more about this, but probably there is some lower limit. 10 to the minus 46 meters of Planck limit is probably the smallest distance you could ever define in the universe. But that's a whole different story. We'll get there later. I don't want to bog you down with that. So there is a reason. There is a reason that we can't divide by 0 because the fraction explodes. But what about the other thing we can't do? We can't take a square root of a negative number. What's the reason for that? There is none. There is no good reason for that. In fact, we can take the square root of a negative number. It's just that the answer is not going to be the kind of number that we're used to. But there's no reason that we can't take the square root of a negative number. And that's what I want to kind of talk about today, is how could we? How could we do that? Here's the problem we're faced with. Okay, we're talking about complex numbers is sort of the title of this section that we're talking about. But first of all, let's do a little review. Let's go back to 5.3 for a moment. Remember what we said about quadratic equations. Let's put this in kind of bigger chapter 5 perspective. Our goal for 95% of the chapter is just to solve quadratic equations. One strategy we had in 5.2 that we probably just soon forget about is factoring. Right? In the case that we've got x squared terms and x terms, then we can factor and set the factors equal to 0. But sometimes we get lucky. Sometimes we get problems like this where there isn't a separate x squared term and x term. There's just an x squared term. And we know what our rule is that we've said all year over and over. If we can point to a single x in an equation, I can always isolate it by reversing order of operations, right? And so in this case, if I reverse order of operations, that tells me the order of the steps I'm going to go through to isolate x. What's the first thing I do? Add, subtract, right? Isolate, I go backwards, bottom up. So I'm going to subtract 10, sure. First step, good. Subtract 10, then what? Okay, multiply or divide by 3, good. Okay, good. Now we're up to exponents. Well, I've got this exponent to undo. How do I undo a square? Square root. We'd have to have a plus or minus there, wouldn't we? But here's where we got problems. Here's where we run into that rule that we've always had, how do we take the square root of a negative number? And until now, we haven't had a good answer. Well, now we do. Here's our answer. We use a different kind of number. We're going to use a number called an imaginary number. Now, that's a really, really bad term to use because it gives the impression that real numbers are normal, and those are useful, and these imaginary numbers are just some crazy thing some mathematicians invented up. But it's not that way at all, I promise you. It's not that way at all. In fact, I want to give you one quick example just to illustrate something, and this is not meant to be something you're going to be doing. I just want to show you something that I can, thinking back to college, some uses that we could put these imaginary numbers to that you wouldn't normally anticipate. The reason we don't use them very much is because they're not good for counting. And most of what we do in life, even algebra, largely is just about counting. We want to solve for x. We want to know how big is x? Well, what number? It's a counting number, right? I could turn it into a word problem if I wanted to. If I have 3 bags of marbles and if I have 3 bags of marbles, each bag has X marbles in it, and all told I have 36. How many marbles do I have? Well, I divide by 3 and find out, right? We could make it a story problem. It's really just about counting. Almost everything we've done has been about counting. But sometimes we don't want to count. Sometimes we want to do other things with numbers. In college, I'll just give you an example of something that's kind of interesting, and I don't want to take up too much time, but we haven't spent, I gotta take some time doing this stuff every once in a while. If you're looking at, say, electric circuits, okay, if you're going to do any kind of circuit design, you want to be a computer engineer, an electrical engineer, whenever you deal with circuits, there are a bunch of properties in the circuit that you have to keep track of. For example, you have to know, if you talk about the impedance of something, it just means how much resistance is there to pushing electricity through it. So every appliance in your house, light bulbs, DVD players, they all have an impedance. You got to know it's got to be set up so that they can be driven by household current. There's a lot of components in a circuit, though. How do you know how to add up all those components in a circuit and find out what the overall impedance is? It's very, very difficult to do if you're using regular, real counting numbers. But if you use imaginary numbers, it is so simple. In fact, you'll do a couple problems and you'll see how easy it is. You can take, there's only 3 kinds of components in a circuit, just resistors and capacitors and inductors, and they each have their own way of calculating an impedance using these imaginary numbers, and it's very simple. And really quickly, you can take something complicated and say, aha, the impedance of that is 24. And that's it. Very simple to do. Another example that came up that I think is, this one always really impressed me in college. If you take something like fluid flow, and math really is about, physics is explained by math. The way the universe works, math describes all this stuff. If you take flow through a pipe, we got a straight pipe, it's really easy to deal with. Fluids, depending on how goopy they are, what the viscosity is. If it's water, it flows real easily, but if it's syrup, it doesn't flow very easily. And the more stickier it is, the more viscous it is, the easier it is to see this. But if you're going to push water through a pipe, it's difficult to describe how that water works. But there's some models we can use that make it simple. One of them is what we call laminar flow. And here's how I want you to think about this. When you help your mom take the recycling back, and you're gathering up all the tin cans, sometimes you get cans of different sizes, and to make things so they'll all fit in the back of the car, you kind of put the cans inside each other, you nest the cans. When you look from the end, you just see like the big cylinder of the big cans, and then smaller ones fit inside, and then smaller ones and smaller ones. That's the model that you can kind of think of for a laminar flow. You can take the water or the syrup or whatever's flowing through the pipe, and you can think of it as being like cylinders of fluid that are just nested around each other. And the reason we do that is because the fluid flows at different speeds depending on where it is in the pipe. Where do you suppose the fluid flows the slowest in a pipe? Just use your common sense. Where do you think it would flow the slowest in a pipe? Yeah, outer edge. How come? You're right. What? Friction. Yeah, it's rubbing against the pipe. The pipe's slowing it down. So that we got this outer layer. If we look in cross section, if I cut through the pipe, it's just right there. If I look from the end, it's just that blue layer, right, next to the edge. And then I'd have one next to that, and so on. Where is the water or the syrup or whatever going to be flowing the fastest in the pipe? In the middle, right? Because that's where it's furthest from the edge, right? Each layer of water is slowed down a little bit by the layer next to it. So say the blue layer is the outside layer. The next layer inside, we'll call it green. It's going to get slowed down a little bit because it's rubbing against the blue layer, right? But if I go inside that, then it can go progressively faster, and eventually the fastest layer is like the lead in the middle of the pencil that just goes right down the middle of this thing, right? Very easy. If I want to know then, if I want to make a prediction about how fast the water is flowing, say I know how fast the water's flowing down here, and I want to know how fast it's flowing at that point right there inside the pipe. As long as the pipe is straight, it's super easy because it doesn't change. However fast the water's flowing right there, it's going to have the same speed right there. Now where this gets complicated is if you go around a corner. If you go around a corner, the water gets jumbled up. And here's why. You know why, actually. Think about your everyday experience. Imagine you're riding on a truck with a bench seat, vinyl bench seat, just been armor-alled, so it's real slippery. If you go around a corner quickly, what happens? You slide, right? You slide. Why do you slide? Because you've got some momentum that wants to keep going straight. If I'm looking down on the truck from above, Now this is gonna expose my limitations as an artist here, but just kind of bear with me. So there's the truck, here's the cab of the truck, right? Tires, tires, tires. But more importantly, here's you, sitting right in the middle of the cab. As you go around the corner and the truck turns, what do you want to do? Well, your momentum wants you to keep going straight, right? And so what really happens is you go straight and the truck turns away from you. And so as the truck turns away, you're going to end up getting pushed to the outside of the car. That's what your momentum does, right? No big deal. Same thing happens in a pipe with the water. Okay, if I send the water around a turn in the pipe, like so, the water molecules that are going the fastest, the little particles of water, are the ones that are going to have the most momentum. Because momentum has to do with with the mass of something, you know, how heavy you are, plus how fast you're going. If you go around a corner really slowly in a truck, do you get pushed to the outside? No, you're not going as fast. So these particles in the center, they're cruising down this pipe. When they hit the corner of the pipe, they want to keep going. The other particles near the edge that are going more slowly, well, they don't have as much momentum, and so they can get pushed aside by the fast particles. And you see that there's some mixing that occurs? This particle is going to get pushed towards the edge. The particles that used to be on the outside, these slow blue ones, get kind of pushed around up towards the middle of the pipe. And as long as it's not too steep, you know, too sharp of a turn, you don't get all this turbulence. And you actually can do some math that predicts, for example, how fast is the water going to be after we go through the turn right there. Only problem is, if I try to do this with real counting numbers, the math is horrible, absolutely horrible. I mean, it would be just literally probably hundreds of pages of algebra just to find out how fast the water's going right there. Really complicated stuff. But you can do a trick with imaginary numbers where you take this pipe, and we're going to talk about this today at the end of the day. I could graph this thing in a way, I could take it from the real world, and I could graph it in what's called the complex plane. In just the right way, so that in that mathematical space, the pipe looks straight, just like this example up here. And in that new mathematical space, in the complex plane, it's called conformal mapping, I could answer the simple question. Well, in this mathematical space, what's its speed going to be right there? Simple. Same as it was right there, right? Get that answer. I'm going to twist that back into the real world by reversing that little trick I used. Take the numbers from the mathematical space and map them back into real space. I got my answer. Simple. So there's just another kind of complicated example, I agree. But complicated example of how you can kind of get an idea how these imaginary numbers we're going to talk about do amazing things. And in fact, a lot of what we do in engineering and physics, we use these more than real numbers. So they're not made up useless things. They're very useful. They're just not for counting. Okay, back to business though. Let's talk about these a little bit. Okay, so what do? Well, first of all, the imaginary unit. How do we deal with this? Go ahead. How do we deal with the square root of a negative number? By just making up a number that stands for that. I. Cursive I, that's not really good cursive I, but it's supposed to be a cursive I, is what we're going to now call the imaginary unit, and it's defined as the square root of -1. It's not a real number. Using real counting numbers, we can't do that, but using this new number that we've just invented, that's what it stands for. The square root of -1, we're just going to call that I, and it really is something. Okay, we can use it to deal with square roots of negative numbers. Okay, so here's how it looks. If I've got the square root of some negative number, where r is some real positive number, and I've got a negative sign in front of it, inside the radical, I can always split this up into two parts. I can split up the square root of -r. I can break that up just like I did before. If I had the square root of 12, I wrote it as the square root of 4 times the square root of 3. Remember that? I can break this up into the square root of -1 times the square root of what?
1.
R. Yeah. And the square root of -1 is what we're just calling I. Okay? So then we get an answer. It's just I times the square root of R. And we can do real problems that way. say we've got something like this, the square root of -3, what do? We just break the square root of -3 up into the square root of -1, which is what? I times the square root of +3 that we're used to. Just the same old square root of 3 we've always dealt with. So the answer is just I times the square root of 3. Done. That's it. It's an imaginary number, but it's the answer to that. What about I times the square root of 4? Break it up into the square root of -1, which is square root of -1, which is I, times the square root of 4, which is 2. Yeah. So the answer is 2I, or I2. Doesn't make any difference. Okay. Okay. And it allows us to. Okay. Something else then. Okay. So we're going to make a little list here. If I equals the square root of -1, let's make kind of a list here of what the powers of I would look like. So I to the 1, anything to the 1 is just itself. That's just I, and that's equal to the square root of -1. What's I squared going to be then? Think about that. What's I squared? I squared is just going to be the square root of -1 squared. What happens if I square a square root? What happens to that? Like square root? They cancel, right? So I squared just equals -1. How about that? That's important. That's going to come up a ton. Whenever you see an I squared in an answer, you can always just trade it for a -1. Okay? What's I cubed going to be? Well, I cubed is just the same thing as saying I squared times I, isn't it? Right? I cubed is just I times I times I. So just I squared times I. What's I squared? -1. So I cubed is just -1 times I. It's -I. Right? Now here's the crazy part of this. What if I do I to the 4th? Now you might be thinking you could do this forever, but no, it gets easier. If I do I to the 4th, that's the same thing as saying I squared squared. It's the easiest way to think of it. What's I squared? -1. Whoops. What's that? -1 squared is what? 1. Yeah. So I to the 4th is just +1. Right? How about that? And then that makes things easy, because if I to the 4th is 1, then I to the 5th is just I to the 4th times I. So it's just I, isn't it? Right? See how that works?
And it just repeats for the rest.
And it's just going to keep repeating. Yeah.
So it's just, so anything past 4, it's just I, whatever equals I.
Yeah. We're going to be able to always go, it's going to go in these cycles. We know then if I kind of split this up, I to the 5th is just I to the 4th times I, which is just 1 times I, right? What's I to the 6th then? I to the 6th is the same thing as I squared, isn't it? Right? See how that works? I to the 7th is the same thing as I cubed. I to the 8th is going to be 1 again. And I could keep doing this over and over again. Right? What's I to the 9th going to be? Same as I to the 1. I to the 10th, same as I squared. I to the 11th, same as I cubed. I to the 12th, same as I to the 4th. Over and over again. So then let me ask you this. How could you do something like, what if I wanted you to tell me, without having to make this table, what is I to the 51st equal to?
-5.
Yeah. How'd you get it so fast?
Because it's every odd exponent is -5.
Okay, because now it's going to go in cycles of 4, isn't it? Right? And so I'd have to make this table go clear out there a long ways, but I'm going to see the same pattern happening. Every 4, it's just starting over again. Well, 4 divides into 51 not evenly, right? 4 goes into 51. Well, we don't even care how many times. It doesn't make any difference. How many times does 4 go into 51? A lot. 51 divided by 4. How many times is it divided evenly? I mean, that's the remainder. 12, yeah. Because we don't care about that, though. We don't even really care that it's 12. We just know that when I divide 4 into 51 evenly, eventually I get to 4 times 12 is 48, and then it won't go in again. What's the remainder, more importantly? Give me 3, right? Does that make sense? Because I goes into 51 12 times, we don't care, but with 3 left over. So I to the 51 is going to be the same thing as I cubed. So the answer is negative I. Right? There's the trick. All you have to do if I'm taking I to some power is just when I divide 4 into that number, what's the remainder? And that's the answer. Okay? So here it is. You know, we can see this pattern over and over again. And there it is. Right? For larger exponents, divide the exponent by 4, then use the remainder as the exponent of I. Okay. So what about that? What do I do with something like that if I want to simplify that? What's the quantity I times the square root of 3 squared? What do I do if I'm squaring, you know, 2 things that are being multiplied? Don't I have to distribute that exponent? So it's going to be I squared times the square root of 3 squared. What's the square root of 3 squared? What's what is it? Square root of 3 squared is 3. Yeah, the square and the square root cancel. What's I squared? No. I squared, that's an important one. What's I squared? Negative 1. So we just get negative 3 is our answer. Okay, what about our example we did earlier that we didn't finish? You told me subtract 10. You told me divide by 3. You told me square root, but then we got stuck. But now it's easy. Yeah, if I see a square root of a negative, that just means I'm going to get my I out front times the square root of the positive, right? No biggie. So I get plus or minus I times the square root of 12. And the square root of 12 could be simplified. What's a perfect square that divides into 12?
4. It's
4. Yeah, I could break 12 into 4 times 3, so it'd be the square root of 4, which is 2, times the square root of 3, so there's my answer. How about that? It's no biggie. Okay? Okay, it's got an I in it, that's all right. Doesn't matter, that's my answer. I'm going to show you, not today, but I'll show you how you can even set up your calculators to give you answers in terms of I's. That's pretty, these new calculators, these graphing calculators, do all kinds of cool stuff you didn't know about. Okay, so complex numbers then. Now here's where we pull this together. So here's something that you've actually used these before without knowing it. Real numbers, think about what we've talked about today. Let's kind of put this back in perspective. Okay, all the numbers we've ever used, we call real numbers, right? Counting numbers. We got these new numbers called imaginary numbers that you've never used before. Okay? But they're separate kinds of things. But it turns out that every number in the universe can be written as a combination of the two of those, called a complex number. Complex numbers have a real part and an imaginary part. And here's how we write them. We write them as some number plus some number times I. So the first part is what we call the real part. The second part is what we call the imaginary part. When you've solved problems in the past and you've gotten an answer, let's say you solved something and you got the answer x equals 3. Okay? What you really meant was 3 plus 0 times I, even though you didn't say it. And why would you? But that part has been there without you knowing it forever. Okay? It's what you had was a complex number that just didn't have an imaginary part to it. Okay? But they're out there. All numbers in the universe are complex, and many of them, in fact, an infinite number of them, have imaginary parts. The one that we just did in the previous example is an example of that, right? We solved a problem, and this time we got an answer that did have i's in it. So that's different than the ones we've had in the past. It's just a complex number that does have an imaginary part. Okay? So how do we do arithmetic? Oh, complex plane. We're almost done for today. There's a lot of stuff, I know, but this is what we got to get through to get to the interesting stuff. So the complex plane. Now, just get this and you'll be good for today. The complex plane just says that we can take the normal number line that we're used to talking about. We've always called it a number line in the past, but you may have heard me call it the real line before. Okay, here's why we call it the real line. All the real numbers that you could ever use are on this line just like they're on a number line. There's 0, there's 1, there's 2, there's 3, there's pi in there somewhere, etc., right? If we put that on a plane and we create another axis that's perpendicular to that, we can call that the imaginary axis. And then we can represent these complex numbers not as being stuck on the real number line, but on this plane instead. Here's what they'll look like if we do that. Okay, here's my real axis, here's my imaginary axis. And if I take a number like a complex number like -2 plus 5i, it's got a real part and an imaginary part. The real part is just the -2. So that's the part that's going to get graphed on the horizontal real axis. The imaginary part is the 5i. So whatever the number is that's being multiplied by I, that's the number, that's where it's going to get plotted on the vertical axis. And so the coordinates of this are just going to be of this first one. It's just going to be at x equals -2, right? Because that's the horizontal axis, and y equals +5. Does that make sense? Okay, so that's how we plot that in the complex plane. What would the coordinates of this one be? 2, 2, over 2, up 2. What about this next one? 4, -3, so over 4, down 3. Last one? Yeah, -4, -3, right? Okay, now what if we want to find the distances to the origin? Because this is an important part of complex numbers. In the book they call it the absolute value. Really it should be called the modulus, but we'll stick with the absolute value. So if I want to know how far a complex number is from the origin, this is important because when I show you guys later in the week, when I start showing you guys these amazing pictures of like the Mandelbrot set, what the colors in the pictures that you're going to see have to do with the distances from the origin. That's how the computer would know what color to create them. It's a little more complicated than that, but that's basically it. I'll give you more details later. If you want to know what this distance is from this point right here to the origin in the complex plane, all you have to do is the distance formula, right? It's easy. This point up here has coordinates, you told me, -2, +5. The origin has coordinates 0, 0, right? And so if I use the distance formula, the distance from the origin is just the square root of -2 minus 0 squared plus 5 minus 0 squared. But we can even do better than that. We can come up with a formula that allows us to not even have to draw the picture. Okay, what if we do this instead? Let's say, rather than pinning ourselves down to just a single point, let's take a point that could be anything. It could be anywhere in the plane. Let's just put it right there, for example. But its coordinates are just going to be a, b, where a is the real part and b is the number that's being multiplied by I, right? The complex coefficient. So if I use that same distance formula, what's it going to give me? Square root of x2 minus x1 squared, right? So a minus 0 squared plus y2 minus y1, b minus 0 squared. And what's a minus 0? A. What's b minus 0? B. So for the complex number a plus bi, the distance from the origin just equals the square root of a squared plus b squared every time. Easy. Okay. All right. So that's the hard stuff. I'm gonna leave off here, but I'll leave you with this one idea so you kind of can see that this really isn't the work will be simple. Adding and subtracting these things could not be easier. The trick is if you're doing any kind of arithmetic, adding, subtracting, multiplying, dividing, treat the I like a variable. Treat it like an x. So if I'm adding these things up, and those were x's instead of i's, wouldn't I just add like terms? I get -1 plus 3 is 2, and 2i plus 3i is 5i, done, right? If I want to subtract, just as easy. All I would do here, my recommendation is just distribute the negative sign. So I get 2 minus 3i, I get what? Minus 3 minus a negative is plus 7i. Add up like terms. 2 minus 3 is -1. Negative 3i plus 7i plus 4i. Easy.
Is this what we're doing on our assignment?
Yeah, half the assignment is just going to be this stuff. So yeah, it's not bad. All right, we'll call her, please. That's good. Okay, we got through most of the math. Now we can start talking about the other stuff next time.